Nice.
So, good morning and welcome to our second day workshop titled Advances in Design, Fabrication and Applications of Freeform Micro-Optics. My name is Pia and I will be the moderator today. The goal of this workshop is to share the excellent work done by the partners at Phenomenon Project and to promote the revolutionary freeform micro-optics manufacturing services by Fabulous Pilot Line, and of course to present applications and the companies that are the reason for these technology developments, who test and give us feedback what the market really needs. We are also very grateful for our special guest speakers who are sharing their insights beyond the EU projects. Yesterday, we started with an overview of the two EU projects. First, Pablo from the Phenomenon shared the project motivations, targets, and some technical results. We will hear more about these project results today. Then yesterday, Rolando shared the concepts of the unique European pilot line Fabulous and its great opportunities for every company in the need of freeform micro-optic services. And as a reminder, Fabulous is open for all your requests and is ready to manufacture both prototypes as well as volume production parts. The second session we heard was very interesting technology presentations from Nanoscribe, Femtoprint, Power Photonics, as well as IMT Atlantique and Multiphoton Optics. Today we have at least as exciting programs as yesterday. We have an honor to hear insights from John McGann, the European Commission's Deputy Head of Microelectronics and Photonics Industry. And during the second session, we will see presentations from Hella, Limbach, Thales, and Design LAB. We close the day with the final words from Rolando and Pablo, the EU project coordinators. And after the presentations, we have the possibility to meet and talk over the WonderMe, the wonderful social platform. The link will be shared over the chat. So let's get started. Our first speaker today is Pablo Romero from Laser Center Amen. Pablo and his team have coordinated the project Phenomenon. Pablo, a longtime researcher at Amen, is involved in many EU projects, and he is responsible for research strategies at Amen. And today we will hear what new opportunities the Phenomenon technical developments are offering for the photonics community. Pablo, the stage is yours.
Okay, thank you very much, Pia, for excellent introduction, which I hope I can live up to. And yes, indeed, yesterday was a very, very interesting day where I just introduced the general concept of the project, and I will now talk about what we have been meeting and discovering during the Phenomenon project, and is hopefully useful beyond the initial scope of the industrial users, and useful to be exploited and transferred to a new range of applications. The project has many EU projects were designed, as I mentioned before, to as I mentioned yesterday, to fulfill a number of applications from our industrial partners. In particular, in these three types of optical structures, we target the refractive micro optics, the diffractive, so wavelength size optics, and nanophotonics, which is sub-wavelength resonant structures and so on. In each one of those, there were a number of interesting applications we target. For instance, the illumination and lighting, which will be mentioned in more detail later on by experts from industry, and concentration PV, which requires micro lenses. Also, diffractive microstructures, we mainly focused on holographic features for 3D visualization. And for display industry, we are looking for mainly flexible OLCD displays, or flexible displays in general, and all the special requirements it has in terms of distributing the light. For all of them, we had to design the structures, design the part, and all the pathway to manufacture it, and as well as specific applications on that, like well, when you have the possibility to make conformal 3D and custom displays or illumination, you can use it for interior parts in automotive, or special surfaces with custom colors and light for anti-counterfeiting and stamping and so on, and anti-fogging surfaces and ultra clean surfaces for surveillance, optics, and security systems and optronics. All this, while very interesting and focusing the most of our efforts initially, was streamlined for our particular end users and a number of industries. Some of them will be explained in more detail by our partners, industrial partners, during the talk today. But in the day of today, as I mentioned also at the beginning of the talk yesterday, I wanted to focus on results that we have been encountering thanks to the technical challenges of the project, and results that can be used in a much wider scope that we think. And I divided those challenges in actually three. Sorry, 1 second. In 5 types of results. So the first type of result I mentioned yesterday is the paradigm itself, also designing simultaneously the application down to its individual working optical structures, the materials, and the manufacturing as an integral approach. And we showed yesterday partially the power of this approach in allowing fast, robust, and efficient manufacturing of novel optical designs. But today I hope I will transmit that even further by speaking of how they interact specifically. And I will talk about the materials, because in this project we thought that we have the materials in the first year of the project, and then we run the rest. It happened that the material was enabler for the structures themselves, for the manufacturing themselves, and also for new concepts. So I will not be able to even show all the advances in materials. The CNRS ENL team was hyperactive in developing wonderful materials. The first one was precisely related with application of massive parallelization. So this is what happened with commercial and standard materials when you try to massive parallelize with tens, hundreds, or thousands of beams very close together. And they develop special formulations, particularly with the new photoinitiators, sorry, that can be insensitive to these nasty effects and can be higher effective, more effective when you try to proceed with massive parallelization. So enabling a new ranges of new ways of fabricating high productivity while keeping very high resolution. These materials also have amazing sensitivity, and not only sensitivity in terms of low thresholds, which allows for larger parallelization number of spots with the same laser power, but also a larger working range. So it means the power where you start writing in relation with the power when the resin start behaving wrongly, like boiling or damage, thermal damage. It's 10 times more tolerant, so larger working window than commercial resists. So it's more robust, and it's something that we wanted also, more industrial in the sense of robust in tolerant environment. And it has a great contrast. So you can go to 150 nanometers apart features with they don't even touch. That's possible even with green laser, which is 520 nanometers wavelength. So it's absolutely impressive what you can do with this resist. Another incredible material that was developed was a large high index up to 2.2 and possibly even higher with more research effort, but very high index material by, well, this was a work using lots of approaches, and the winning approach was combining ceramic nanoparticles with specially formulated resist to produce a high sensitivity and a resolution resist that at the same time has this refractive index. So you can now direct write any shape with down to 100 nanometer line width or resolution, and with fairly short spacing. So quite a lot of freedom of design of your structures. And after pyrolysis, you have this enormous index and index contrast with air and with your substrate. So you can have a whole new range of optical design that I will show later. And the resist is also very stable, even at very high temperatures, because it's ceramic after all, and has low shrinkage, and it's mechanically very good. So it can be directly used for stamps, for polymers, or for UV curing, for a number of things. Another also incredible material was and completely unexpected in the initial writing of the proposal, nonlinear formulation that can be used for continuous wave writing and very low energy. So this is perfect for large area photoplotting and opens a new way of manufacturing, also with projection optics and other types of approaches, which are not simply femtosecond lasers, CW lasers with low power can be used for 3D writing, high resolution optics also. Something that we consider also an outcome is the optical design we use for manufacturing, which are a number of them, more or less complex and at lab scale, but this has already been also transferred to industry, to multiphoton optics, and to ourselves. We are kind of semi-industrial. IMAN is kind of semi-industrial research facility. So we consider this also ready for transfer to industry. So you get in contact with us if you want to use a combination of phase SLM projection, scanning optics, and DOEs in a new way for your applications. It doesn't have to be in two-photon polymerization. It can be in other applications also. So design methods and software is another secondary outcome of the project that also has very attractive market potentials for us. So the company in charge of the Laos software, FluxSim, developed this special optic module where you can generate your optical layer structure. So where is your illumination and light guiding and light extraction and so on, but also generate on them arbitrary textures and geometries, and on top of that bend or give it a shape, and then you will get a simulation of the polar distribution in all wavelengths of your part. So it's a very powerful tool for designing optical structures on complicated shapes. And we did that because we needed it for designing one application that will be mentioned later. But it resulted in a already commercial product, which is this Laos optic, which can be used for any kind of optical design beyond the typical multi-layer approach for designing, for instance, solar thin film for solar assemblies or displays. There was also a method for designing structures based on dielectric nanopillars, the dielectric elements, by very, very simple discretization of the faceplate or the phase distribution into individual elements. And I will show this how it's extremely powerful in generating any kind of optical function. In particular, we used it to generate a hyperbolic microlens, difficult to produce as freeform and normally high aspect ratio. We did it in sub-micron film, so ultra thin optics generated by thousands of micropillars. And the question is the diameter of the macropillar, which can be controlled by a single exposition with different energy, controls the the phase. So we generated um, the the optics directly by multiphoton optics did the job voxel by voxel by as a completely planar structure and confirmed as 60 micron lens diameter with 30 micron um, focus length and very high over one numerical aperture. So very powerful optics. There are other types of optostructures, like fully 3D optostructures that generate structural colors and color holograms, planar structures, thanks to high index contracts that generate polarization control, color filtering, or micro lensing. So lensing with also high numerical aperture, very short focal length, or structures that make light guidance and light extraction at the points you want. With that, we constructed the sixth type of results I will mention, and I will end with this, which is custom optical surfaces built with all the previous results. For instance, customized optical surface diffusers and light extraction for illumination with this type of non-periodic prism films that are very powerful in distributing light. Light extraction with a very customized distribution for these curved films, so you get more light or less light when you need and in the direction you want for the viewer of these curved displays. Or anti-fogging super hydrophobic surfaces that can be used for a number of optical applications that you can see. It's very effective in keeping dry the optical windows that can be done directly through direct writing with multiphoton polymerization, through writing and etching, or through soft lithography or replication techniques, but starting with our technology. All those, we think, are results that are immediately usable in a very wide range of applications. And in this meeting, I hope there will be ideas and propositions on how to use it in future projects, future products, and new types of applications. So beyond the demonstrators of the project, which are available in the website of the project, that you can click here, you have the possibility also of contacting me for these other types of results, individual results that are available for further development and investigation. And I totally confident that we will spread into a big number of new possibilities in the near future. So that's all from my side. I have to acknowledge, of course, the European Commission for the financial support, and not only financial. They were very supportive during the 3 years of the project, and all the excellent partners in the project for their results and their continuous work here. So thanks everyone also for your attention.
Thank you very much, Pablo. I agree, this project was really amazing. And I think a lot of the partners also said that this was one of the best works they've done in any of the EU type of projects. Sana had a question asking, what are the future plans for Phenomenon? Where to get such an services after now the project has ended?
Yes, we are not as fabulous a project is a project with a structure of services after the project ending. We have ended already last month, so the project is effectively finished. So you can contact individually the partners. Each partner is owner of their own individual results, and the industrial results that will be shown later on in the talks have ownership of the industrial partners. So they are the ones who can provide the possibilities there to extend to a license or whatever. The problem is many results are really interlinked effects of many partners working together. And we will be very happy to work together with anyone wanting to implement those results that were the last ones I shown in any applications which is different from the ones from the end users in the project. So simply contact me, and I will get the partners to work together with you, because all of us are really excited to bring those results to applications. So yes, just contact me.
Then maybe I also want to just briefly also acknowledge Patrice Baldec, and who was working on with the materials. Patrice is also participating. So if you have anything material related questions, you can chat with him or get in touch with him. So Patrice, is there a word if you want to say something also about the team's work? You're more than welcome.
He's shy today.
But Patrice, anyway, magnificent work from the team.
I agree. He and his team also was a great enabler for the whole of the project.
Yes, but I think we need to move on, and I want to now have an honor to welcome the next guest speaker, John McGann, and he's the deputy head of the microelectronics and photonics industry at the European Community, and he will share his European photonics insights. And I think we're going to hear also some tips for the upcoming photonics calls. So please welcome, John, and we are very much looking forward to hearing your presentation.
Thank you very much, Pia. And first of all, congratulations to Pablo and the rest of the team there, because I think this is a beautiful example of a project that's not only cutting edge, but integrating lots of different technologies and bringing them all together in a very fruitful and innovative way. And this is exactly the kind of thing that we're trying to support here. And I'm going to try to give you a quick overview and some examples of what we're doing now and trying to look to in the future. So the first thing I should point out is that we have, as an example of the integration in the technologies, we've also had some integration within the European Commission. So the photonics and microelectronics units have been brought together into a single unit, microelectronics and photonics industry unit. And this is a nice example of the convergence of these disciplines. And we still have as much support for both sections, but we're trying to, in this way, have a better integrated approach to these different disciplines. So next slide, please. So just a quick outline of what I'd like to talk about today. First of all, just to talk a bit about the integration of the technologies that we're covering in the unit. And then I'm going to try to give you a bit of an overview of Horizon Europe so that you can find your way around it, and particularly find your way to getting some funding in our area in digital industry and space there. And then I'm just going to briefly elaborate on the main photonics topics that will be open for proposals in the next 2 years in our current work program. So next slide, please. So, of course, being bureaucrats, and especially being Eurocrats, we don't make life easy for anyone. We've got lots and lots of jargon, lots of acronyms, and I've just put some of the ones that you might come across up here, and just as a way of pointing out which ones are the most important to find your way around. So we have things like important projects of common European interest, IPCEI, which a lot of the European industry is getting interested in at the moment, and we're trying to set that up at the moment. We have the Digital Europe program is DEP, and this is all funded under the Multi-Annual Financial Framework, MFF, and we have the Recovery and Resilience Fund, RRF. But the two that are most important that you need to remember are the HEU, the Horizon Europe program, which is the new research program that I'm going to be elaborating on. And linked somehow to that, which I'll mention at the end of my presentation, we have a joint undertaking on key digital technologies, the KDTJU, and this is the successor of the Excel joint undertaking that some of you might be aware of. And this is where the Commission, the member states, and the industry all come together to form a joint undertaking to fund more mature research and innovative projects. Next slide, please. So this integrated in diversity. So it's in a way our new motto for the unit. This is a concept that's been elaborated by my colleague Henri Rajbenbach. So if you have any difficulties with it, you can approach him on that. But it's an example of how we're trying to integrate the different technologies together in the unit. And these are mostly hardware type technologies. Photonics we have at the top, at the forefront. So we're talking about both active and passive photonics. So not only sources, detectors, modulators, and silicon photonics, but also passive components and devices like waveguides, fibers, but micro and nano optics, which probably of most interest to the community here, refractive and diffractive optics, and so on. And but not only these technologies, these have to be co-designed with all these other domains such as micromechanics, microfluidics, and so on. But the two, oh, sorry, can you go back, please? Yeah. So the point is that it's not only photonics, it's not only micro and nano electronics, but we're trying to integrate these with all these other technologies in a co-designed and kind of holistic way. Not only for design, but also these then have to be miniaturized and packaged so that the ultimate concept is to end up with integrated digital components that for a multiplicity of applications. Sorry, now you can go to the next slide, please. So this is just to give an idea of the kind of specifications that we're trying to achieve in these areas. So it's a very dense space. And the example in photonics, we're talking about the sources and detectors. We need to be dealing with concepts like the spectrum, the bandwidth power of the emitters, the sensitivity of photodiodes, or the multispectral aspects of the optical sensors, including the image sensors. But also in other things like in microfluidics, we're talking about the gas or liquid flow rate, minimum volumes to operate with. Then in sensors, it's the true positive and true negative rates, and so on. So just if you can click once more, and again, and once more. Yes. So really what we'd like to aim for is in terms of size and cost. we're talking about integrating all these in about, for a cost of about €1 for a cubic centimeter, just to give a ballpark figure of the kind of components we're talking about, or about $1 or €1. A dollar bills in terms of size and cost for flexible and wearable systems and patches. So this is just to give you an overall concept of what domain we're in. So now I'm going to move and try to untangle some of the complexities of the Horizon Europe program. So this is a 95.5 billion euros that we program arrived at after a lot of political wrangling. The most important side of it is this pale blue one, the global challenges and European industrial competitiveness, and that has 53.5 billion euros here. So that's so you can find your way around. That's the so-called Pillar 2. Next slide, please. So in this Pillar 2, there's several different domains that are addressed, and these are, unfortunately, we've got a lot of jargon. We're in what's called Cluster 4, which is dealing with the digital industry and space. So that's important to remember. So Pillar 2 and Cluster 4 for the areas of interest for this community, I would say. There's several other applications that could be of interest and relevance, such as health in particular, also the food and bioeconomy, climate. Some of these areas will be also supporting applications, which could be, so your technology solutions might also be of interest there. But in the digital industry and space, we've more a technology push rather than the application pulls type of topics being called for. So next slide. This is just another way of showing this with the different budgets, so we don't need to dwell too long on that. I'd rather go on to the next slide again, please. So drilling down inside Cluster 4, we have I'm afraid, some more jargon. So the sub areas are called destinations. Please don't shoot me. I am not the one who came up with this way of describing things, but the idea, I think they wanted to differentiate it from topics that were being called for in the previous program. So the important thing to remember is these destinations are overall areas. So, and the destination of particular interest for us, that includes photonics and electronics, is the digital and emerging technologies and for competitiveness and fit for the Green Deal. And that encompasses these more technological areas that are of interest here. Next slide, please. So within digital and emerging technologies, there are 6 topics covering photonics and microelectronics. And I'm going to be dealing, sorry, yeah, thank you. So the 3 of most relevance for us are on photonics, which I will be elaborating in the next 3 slides. So next one, please. So the first one, now this is really building on the original reason for having photonics in the IT programs, going all the way back to the 2nd framework program and the Esprit program, was that photonics was really for telecommunication applications. And so this is really a successor for that very long and noble pedigree. And so here we have a 26 million euro budget for that is being called for. We are expecting projects of a size between 4 and 6 million euros. Although it can be bigger or smaller depending on the application, but these are our guidance. And this topic is being called for already later this month on the 22nd of June, with a deadline in October. And here what we're trying to look for are a new generation of technologies for for optical communications with reliable and low latency communication, reduced congestion, especially when we've got multiple applications being used, reducing power consumption, because this is a very critical criterion, and reducing the cost to about 50 cents per gigabit per second. So to try to drive down all of these. The scope here is in ultra-dynamic photonic components and systems for communications, in new wavelength bands, and also enabling ultra-dynamic reconfiguration on the optical layer. So the idea is to have it as flexible and dynamic as possible. The range of use cases can cover everything from optical switching in commercial applications, but also for more general industrial applications. And so not only broad and long distance datacom and telecom, but also industrial applications, and where you would need very, very high bandwidth, very, very high rate of communications. So next slide, please. So this topic is more on advanced photonic integrated circuits. And this is, here we're building on the excellent work that's already been done and going on in the PIC, or photonic integrated circuit pilot lines, that we've been supporting over the last 10 years. And this has been highlighted and indeed showcased by EPIC, our hosts today, because they have a range of conferences directly addressing PICs. So, and I guess many of you might be of interested in those. And here we've got quite a sizable budget of 39 million euros available. We expect project sizes to be somewhere in the range of 3 to 5 million euros each. This is also opening later this month and closing on the 21st of October. And here we're really talking about new generations of PICs, strengthening the industrial capacity, lowering the barrier for their use so that these can be taken up by high-tech SMEs. And so to really broaden the range of applications and the use of PICs, and also to provide European strategic autonomy in these, but not only in the technologies, but also in the related manufacturing processing, because we need not only to, because as in so many other areas, you know, Europe can often lead in the technology, but then somehow fail to make the transition to having the manufacturing capacity in Europe. And here, with the pilot lines already operating, we were trying to overcome, to make sure we don't fall into that shortfall again. And so that's why the manufacturing is critical. So it addresses integration. It's, as I say, trying to aim for entrepreneurial SMEs and get new paradigms. So extending the functionalities through co-integration of photonic and electronic components. So again, we're going back to the idea of integrating and bringing diverse technologies together, because that's where the real interest and the real innovation comes. And so next slide, please. And here is a nice example of the integration of technologies. So one of the main uses of our technologies, of course, is advanced multi-sensing systems, or sensing. So here we're trying to do advanced multi-sensing systems and bringing together photonics, electronics, and other technologies. And again, the idea is to have open strategic autonomy in Europe in these technologies, and having sensing devices to help reach the new Green Deal objectives. So we want to reduce overall power consumption in systems by at least a factor of 2. But we imagine that in many cases, the new proposals and the new research will be able to go for much greater energy savings. So, but a factor of 2 would be at least a minimum, we would say. And of course, we want to reinforce the industrial leadership in these areas. And we're expecting breakthroughs through the integration and combining the different systems integration and so as to handle a vast amount of sensory data. So the idea is that this will be the eyes and the ears and the nose and whatever of edge computing and the cloud. So, but integrating and processing as much as possible, as close to the sensors as possible, rather so as to have a higher capacity and also a lower energy use. And we would like, as far as possible, to also that a modular approach could be adopted here. So the idea is not to have individual bespoke components, but things that are interchangeable on a platform, so that they can be more future-proof and be capable of being replaced and in particular upgraded in the future. Okay, thank you. And next slide, please. So apart from these areas that I've mentioned that are in Horizon Europe, I would like to just stress that there's other areas that of interest and that could support the work that you might be interested in. I mentioned the key digital technologies joint undertaking at the beginning. This, as I say, is the successor of Excel, and where with the more industrially focused and the higher technology readiness levels, more mature technologies would be supported. And here, optical interconnects and integrated photonics will also be supported. So I would encourage you to look there too. But then there's other parts of the Horizon Europe program, such as mobility and industry. And here, for example, we would expect the photonic technologies like to be applied in sensors, LiDAR, etc. There's also a large budget available for quantum technologies. And here we would expect things like tailored photonic integrated circuits, quantum PICs in essentially to be covered there. So that could be another area of interest. Then in health, there's a lot of applications for photonic technologies are in the health and biosciences domains. So we'd expect support to be there. And then last, if you've got more mature technologies or are trying to make the transition from research to deployment and commercialization, there's the European Innovation Council, and there's 3 different schemes that will support work such as the Pathfinder, the Transition, and the Accelerator Actions. And these are designed to take advanced research at different stages and help them to get through the valley of death and for deployment on the market. Next slide, please. So if you want to find out more about any of these things, I mean, you feel free to contact us in the unit, but I would encourage you first, though, to have a look at the Horizon Europe website where you can get information. What I presented here was just an extract of the work program, so you need to have a look overall there. The tools are a lot better for trying to find your way around and trying to find the right area for support. And especially in this European Innovation Council as well, they have a wizard there for helping guiding you to the right area of funding. There's the European Research and Innovation Days are coming up very soon, and I think you can still register to participate there, and there will be possibly some opportunities for networking online there. And then finally, I'd like to just mention the Photonics 21 Association, which has also got a lot of showcases of different projects. So if you want to check what's already been funded, nice examples of projects, and also areas that you could maybe build upon for the future. Okay, so sorry, that was a bit of a rushed presentation through there's so much that we support, so I hoped I got the right balance and without being too dull. If you have any questions, feel free to ask now or to follow up bilaterally in the future. So thank you, and back over to you, Pia.
Thank you very much, John. What amazing presentation. I think you help us to translate some of this jargon, as you say, and also it was very good to hear, to see what are really the targets and the integration of these different sectors. I think we are a little bit behind the timeline, so we have one question on, let's try to tackle one of them. So John, there's really no clear opportunities for VR, AR, mixed reality technologies in Horizon. Do you know if there will be any specific programs for this market share?
I don't believe there's a direct application, a technology topic there, but I think they will be supported indirectly as part of the work in that area. But what I don't want to give a waffle answer. So what I would suggest, Ruben, that you do is to contact me bilaterally, and I can certainly direct you to the colleagues, and I can make sure you get a proper specific answer afterwards.
Thank you.
Any other questions? But I would say then let's thank again, John. Really very insightful presentation, and we are so happy and honored that you could join us here today.
You're very welcome. It's a pleasure to be here. Thank you.
So let's move on to the next presentation, and that will be Daniela Karthaus from Hella, the German automotive supplier for electronics and lighting. Daniela is an optical designer, and she has an exciting job at the innovations department focusing on micro-optics. So Daniela, the floor is yours.
Thank you very much for the introduction. So let's have a look from the presentation. So hopefully it works. So I have now also some windows here that won't disappear. I hope this should be no problem, I think.
Your presentation is perfect.
Great, okay. So then, yeah, thank you again. So today I have the chance to talk here a bit about our chances and challenges regarding micro-optics and automotive applications. First of all, I'd like to start with a short introduction to our company, Hella. Hella was founded in 1899, and today we are one of the leading suppliers in the automotive industry. We have more than 125 locations in about 35 countries with around 36,000 employees worldwide. And the product portfolio is separated into 3 different segments. We have automotive, aftermarket, and special applications. And today we will focus on the automotive segment. And here you see some of our products that are developed there. We have exterior lighting, light headlamps, rear lamps, and car body lighting. We also look for interior lighting. And of course, an upcoming important point is the lighting electronics, to be able to control all these adaptive lighting functions in and around the car. And of course, the topic of radomes as a kind of intersection to sensors. So let's start with the motivation for using micro-optics in automotive applications. So within the last years, we see a clear trend, or we see different clear trends that require the reduction of optical components. One is, for example, the miniaturization of light sources. So in automotive industry, we typically use LEDs. And as you all know, these LEDs are getting smaller and smaller, nearly keeping the same performance. So to take advantage of these developments, it's necessary to reduce also, of course, the optical system behind these light sources. Now, the second point is the reduction of installation space. When we look at new applications around the car, you see, for example, here an image of a light carpet. Then we have new areas, new spaces in the car where we need to integrate these optical systems. And of course, we need to look for a real compact system for these applications. Then a great trend is, of course, the styling. So you see an image with an example. So in general, we see that the styling requires really small and slim and thin lighting applications, luminous surfaces, and also for the rear lamps and the headlamps, really small and slim light exit surfaces. And therefore, of course, we need to reduce the optical components to fulfill these styling requirements. And the last point is digital light. This means that we try to realize really high resolution adaptive driving beams. And of course, therefore, we need a lot of light sources or specific optical devices, which of course needs to be reduced in space to fit into the installation space again. So let's come to the chances. There are, of course, different advantages regarding micro-optics. The first one is, of course, the reduction of the thickness, the weight, and the material consumption. When we think about classical optics, which might be in the area regarding the thickness of several centimeters, and we replace them with micro-optics, we are able to reduce the thickness drastically to some millimeters. Of course, regarding the substrate that is necessary for the microstructures and the like. And of course, therefore, we can reduce a lot of weight and also the material consumption here. Then we are able to match with the new styling options that I already mentioned, like the thin light exiting surfaces, but we are also able to use micro-optics for beam shaping elements. You see here an example where we used a micro diffractive diffuser optics to generate really specific geometric signature. And this is, of course, a great possibility to generate new styling possibilities. And on the other hand, besides the beam shaping, we are also able to have homogeneous luminous surfaces. And here is one specific advantage, that we are able to increase the efficiency also. When you look at the image here in the middle, at the top, there we have signature that is generated by an LED array, and of course it looks really spotty. So typically we would use then volume scattering optics to generate this nice homogeneous appearance. And we can also use, that is shown at the bottom of the image here, LED arrays with micro optics. And you see it by the color that is indicating the light intensity here, that we have a higher light output with a comparable homogeneity. And this is, of course, a great advantage, that we can have diffused light, but also can control the direction of the light and the emission angle really nicely. So when we look at our latest developments, with the combination of micro optics, then we have, for example, the Hella flat light module. Flat light is in general, a wording, and we have several technologies that can be used to generate really homogeneous appearance with a really slim and thin package, as you can see by the images here. And the micro MX concept that is shown here in the images is using an optical stack with different optical layers, and each layer consists of a one or double-sided micro optic, also freeform micro optics. And in combination, we get this really nice homogeneous appearance with a good, really good efficiency. And we can also use this technology for tail lamp, stop lamp, and also turn indicator. For the headlamp systems, we have a look here at the Fabulous project. Here we are one of the use case partners, and our target is to generate double-sided freeform micro-optics for headlamp applications. So on the one hand, again, the styling aspect, that we want to have really slim light outcoupling surfaces. And on the other hand, of course, generate typical light distributions as they are needed for headlamp applications. Okay, at this point, everything sounds really great, I think. Let's come to the challenges now. So as an example, you see here in the image on the right side, a section of our design that we are looking at in the Fabulous project. The single facets that are shown here are in the range of 100 to 150 micrometers. And yeah, this is an example for a freeform micro-optic that we are focusing on. And what we already, on the left side, you see the requirements that we already addressed in the Fabulous project. So on the one hand, of course, we need a really high optical surface quality because we have an imaging optic here. And this means that especially each facet needs to have a low deviation concerning the design and the manufactured element, of course. And we need a really good optical surface or a low surface roughness, let's say. On the other hand, as I mentioned, we have really small facets, but a relatively large optical element in sum. So overall, we are in the area of several millimeters, up to 100 millimeters in one dimension. And then we have, of course, a lot of data information here, and the data handling for these elements is also a challenge that we are looking for. Typically requirements we have in the automotive industry is the cost effectiveness of the mastering and the series production. And we need to use, of course, automotive certified materials. This is a really specific topic, and I will come back to this on the next slide. Maybe one additional point that we are not focusing in Fabulous currently is the topic of 3D curved substrate. So typically our products and thus also the optical components need to follow the vehicle contour, the vehicle curvature. And therefore, of course, we need to have the possibility to generate this micro-optics on 3D curved substrates. And you see here some examples of a 2D substrate of 2.5D and 3D substrate. So 2.5D means curved in one direction, 3D curved in two directions. And of course, this is a target that needs to be received. So finally, this is already my last slide, but I think a really important one, especially concerning the challenges. So in the automotive applications, we have really tough conditions that you can see here. We have a high temperature range from -40 to 120 degrees, of course, a little bit depending also on the application. We have gas exposure, fuel, saline water exposure. So UV sun radiation, of course, is one really important aspect. So it doesn't mind which material we need, or if we have two materials that are combined or whatever. So we need, in any case, to avoid deformation when the material is getting in contact or is exposed to these conditions here. We need to avoid delamination, and of course we need to avoid discoloration. So this is really a great challenge, especially when we look to the combination of automotive qualification of the materials, and of course the manufacturability of the materials in the typical micro-optical processes. So I think with that, I'm already on the last slide, and I thank you very much for your attention, and I hope you have some interesting topics to ask or maybe some comments. Thank you.
Thank you very much, Daniela. What an interesting presentations. And as we know, the lighting has become more and more bigger thing, a topic in the automotive. It's no longer the functional, but it has so many more elements. Any questions for Daniela? So far, I did not see anything on the chat, but
we have a question from SUS Micro Optics.
Ah, yes.
You are unmuted. Yeah.
Thank you. Hello, Daniela. Very great talk. Very impressive, your progress in the flat lights. Could you elaborate a little bit on what technology is used for the flat light? Is that injection molding or roll-to-roll or something? Can you shed some light on how you do that? You said it's also double-sided. Is that correct? Did I understand that correctly?
Yeah. So there are different layers. I don't have the exact number right now, but we have several layers. some double-sided, some one-sided, and we are looking for different possibilities here because, of course, each manufacturing process has its own advantages and disadvantages. So if we look on the one hand of a kind of nano imprint technologies, but we also look for injection molding technologies that are able to generate these really small microstructures on really thin optical layers. It's both. We look in many directions for that.
Okay, thank you.
You're welcome.
Any other questions for Daniela?
Yes, François Lebel here from Dow. Quick question on optical material. I mean, do you use a combination of material? I mean, for controlling the light at the microstructure levels, or? And you also referred to automotive certified material. What do you mean by that?
Yeah, automotive certified means for me that on the one hand, we need to fulfill all the requirements that I mentioned, of course. We have different tests for that. And on the other hand, when we look for different areas where we want to sell the products, then we need to take into account also these requirements we have there. For example, the Amica listed components and the like. Yeah, this is also important, of course, for us. The question you asked before, sorry.
Yeah, combination. I mean, because to make these micro optical structures, maybe you need to, I don't know, you mentioned delamination. I don't know between what and what you refer in terms of delamination. What do you mean?
Yeah, in general. So if we, for example, have combination of a substrate, for example, PC layer, and then we have a kind of UV resin on it, then we need to avoid that this UV resin is delaminated during lifetime and during especially all the requirements I mentioned. Yeah, and therefore, of course, we look for different possibilities, which is the best substrate here. Of course, we try to avoid glass because of the weight. Yeah, there are a lot of different UV resins and the like that could be used, and yeah, this is an open point.
Okay. Okay. Right. Okay. Yeah. Thank you.
You're welcome.
Thank you, Daniela, very, very much for your presentation, and we are very thankful that you were part of the workshop today.
Thanks a lot.
So let's move on to our next speaker. Ruben Mohedano comes from an IP company, Limbach. That's where the team has developed an advanced optical concepts. We are very much looking forward to hearing on Limbach's thin lens concept designed for VR headsets. And Ruben,
sure.
The stage is yours.
Okay. There we go. Can you see my screen now?
Yes.
All right. So thank you for inviting me today. I'm going to talk about how we are striving to achieve headsets with the size of sunglasses. I'm Ruben Mohedano. I'm presenting this on behalf of the team at Limbach, working on this concept that we call Trenza, and that we are being able to develop thanks to our participation in the Fabulous project, as you will see later on. So this is the outline of my presentation. I will go to an introduction. I will first talk about 4-channel optics, and then we will go to multi-channel optics and MLAs, which is the main topic of the talk and our work in Fabulous. So if you look at the basic design in VR, you basically have a lens in front of a panel, a display panel. This lens projects the information on the display panel onto the user's pupil. And then if you design the optics the way you had to design it, you can achieve the resolution, the field of view, the efficiency and depth that eventually leads to the headset features. Basically, you need to project the information in a very wide field of view, 90 degrees at least, so that you can feel really immersed in the experience. When you do that, the resolution is rather low in pixels per degree in the angular resolution, because you are kind of stretching the pixels of the display into a very wide field of view. So you can see the pixels, and you see the resolution is quite low. You have this screen door or chicken wire effect that is very cumbersome. And also because conventional optics is not able to do very fancy things, and the headsets are very bulky because you have to locate the display very far from the optics and very far from the user's pupil. So this leads to the two main problems of VR headsets these days related to hardware. That is, both are compromising the user experience and is maybe preventing the mass adoption of these devices. So low resolution, bulky size, and heavyweight headsets. This is what you see in all these commercial solutions, Facebook, Oculus, PlayStation VR, HP, and many different devices. So what we do at Limbach is try to, inspired by nature, follow a different approach, splitting the optics in different channels, like the eyes of insects, and process the light in parallel. By using this type of approach, we will be able to locate the display closer to the eye and then reduce the size of headsets. And we will have to face the challenge of keeping the resolution or even increasing the resolution. So what we do is basically, this is the original design. If we split the original lens into two, you now process the light in parallel. You can use a smaller display and locate the display closer to the optic. And if you keep on adding more lenses, you can get the display even closer to the eye and then eventually reach the size of sunglasses. However, this approach of splitting the light into different channels will have a problem with resolution, because you will have to apply some redundancy in the information that you display on the panels. You need to duplicate many pixels showing the same information, so the apparent resolution eventually drops. Let's go to a first example using 4 channels. Is a commercial product that we have that we call Clover, using the name of this grass that only has 3 leaves, but everyone would like to find one having 4 leaves. So this is the Clover having 4 segments, totally freeform. And thanks to this technology, we are able to reduce the size of the headsets by a half. So the total track length, the distance from display to the eye, is reduced down to a half. This have an impact in the volume, obviously. And then by using this technology, we are using the skills or the power of different features. As you can see on the drawing below, we are using a light folding scheme that is able to bounce the light very efficiently by using mirrors and also total internal reflection in a monolithic part, totally freeform, that allows us to locate the display very close to the optic and produce an effective, very large focal length in a very reduced space. So the total track length is very short. And we are still producing the field of view that we need and the resolution that we need. This device is shown on the left. It's been designed and later prototyped using plastic injection. So it can be done in one shot. And then you had to apply some metal coatings on the front and back surfaces to be able to produce the performance. As you can see on the right-hand side, thanks to this technology, we are able to keep the resolution and the field of view, but the depth is greatly improved. So here, the original depth of, as you can see, we are here representing the inverse of the depth. So when you grow on this axis, it means you are better. So you start with 50 millimeters depth for a conventional system, and we are now in 21 millimeters. So we are greatly reduced the size of the headset. You can see the magic of these 4 segments operating. is that when you are looking through the lens, you see one single image, okay? But actually, in the display, there are 4 images. You see, so these 4 images projected through the 4 freeform lens are welded into one single image, perfectly stitched and seamless. So you can enjoy the virtual reality scene without noticing there are actually 4 segments in the optic. This device is going to be featured in one commercial product very soon by a company called Lynx in France. And as you can see here, the size of the headset is greatly reduced compared to conventional headsets. So we can now go to more channels, and then we had to deal with this redundancy problem. Landman was a pioneer in this field. When he was at NVIDIA, he developed a system based on mini lens arrays, and he was trying to solve the divergence accommodation conflict, and he was producing an image thanks to an MLA array that was very poor in resolution, only 5 ppds, and short in field of view, only 30 degrees, but the depth was impressive. As you can see here, only 5 millimeters. His work was amazing. And because of this usage of mini lens arrays, he had to, as you can see on the image, duplicate many pixels in order to show the virtual reality scene in the right way. But the size of the headset, as you can see on the left-hand side of the prototype, is super small. So we are developing a technology called Trenza that is trying to counter this resolution loss effect, recover the resolution, and try to achieve 30 ppds. This is very good. Conventional headsets these days, probably most of you have tried some of those, are in the range of 15 to 20 ppds. So we are targeting 30 ppds, which is better than that. And we will try to get the field of view, so you get the presence feeling, which is a must in virtual reality, so you feel really immersed, and keep the very reduced depth of this Landman approach, so down to 80 millimeters device. How we can deal with that? So the key to not lose the resolution and even increase the resolution is on the first, first is using freeforms in the mini lens array. So you cannot use a rotational isometric identical lenses in the mini lens array if you want to keep the resolution high. So we will have an array of lenses being freeform, all of them, and different from each other along the area of the MLA. The other technique that we use is what we call passive foveal super resolution. And basically, when we design every lens and when we design the entire layout in the mini lens array, we take into account how the human eye really works. And we know the human eye is very picky and very sharp, only plus minus 3 degrees around the gazing direction. So you can focus very well only in the directions you are directly gazing, but around those directions, everything is kind of blurred. So you don't need to, when you do the design of every lens, you can take that into account and do optimize only for gazing directions. You forget about the peripheral angles. That gives us room for increasing the apparent resolution in the design. And the third concept is something that we cannot disclose in detail here. It's what is more magical about this device is what we call pixel interlacing. And it's a smart combination of the way we present the information on the display and the way we arrange the design of lenses in different groups throughout the MLA, so that you produce a kind of pixel interlacing effect, increasing the resolution by a factor of 2 linear. We had to test if this interlacing effect was something really achievable, and we did it with a simple MLA, an off-the-shelf array that we bought. And we produce a proof of concept only producing the interlacing, so no freeform lenses, no passive foveal resolution. And we were able to increase the resolution from 5 ppds up to 17.5 ppds only using interlacing. As you can see, the contrast is low because this was an off-the-shelf MLA, not very well manufactured, but the resolution increase thanks to interlacing was there. So now we are working at Fabulous and challenging the pilot line so that we can test whether using this entirely freeform mini lens array can produce the type of performance that we are aiming. And we are now at the stage in which we have the first samples of masters to produce our parts, and they have been done by UPMT in Belgium. They look very fancy and nice. And the parts will be manufactured by SUS Micro Optics. And we expect to have some results soon so we can start doing the test and see whether this really works. So with Fabulous, we expect to have a demo by 2022, having these features, 26 ppds, 80 degrees field of view, and a superb 80 millimeters thickness. By 2023, if we are able to use a custom display, not an off-the-shelf display, as we are going to use in 2022, and by adding eye tracking and myopia correction, we will have a better version of Trenza, and later on we will work on higher resolution devices, versions accommodation conflict free, and also we will try to achieve a higher field of view. This is the roadmap for Trenza. So this is how the prototype of 2019 looks like, and the Trenza product would produce a performance achieving more than 30 ppds. This is a simulation of how this will work, and we expect to have nice results by then. So as conclusions, I would like to emphasize that multi-channel optics are enabling high efficiency in a very reduced space, and then is likely to produce headsets for virtual reality and augmented reality with the size of sunglasses. The freeform surfaces in the MLA are a must if you want to get the best image quality and the angular resolution to have a nice user experience. And we are currently vetting the freeform mini lens arrays manufacturing technology within Fabulous. With that, I thank you all for listening, and you can contact me at this email address anytime. And thank you again.
Thank you very much, Ruben. What an interesting presentation. I truly found it amazing how you have increased the optical path by this folding. This was really brilliant. And of course, also amazing how you stitch the images. Fantastic. I also have to say that in my opinion, all your optics, they look like a piece of art. And I think one way they really are. I wanted to see if there are any questions. Perhaps you can also start no longer sharing your screen so we can see the participants. If there are any questions from the audience.
Actually, if you don't mind, I would find it very nice if Rolando, are you in the room? If Rolando, the project coordinator of Fabulous, give a word. So we had an introduction about Fabulous yesterday, and Fabulous, the pilot line, the European pilot line for freeform micro optics that started in January 2020. And we have here in the room more than one partner in this project, in addition to Limbach as a use case. We have also SUS Micro Optics, CSEM. Let me see who is in the room who would like to share their experience being a partner of Fabulous. Otherwise, you can also contact me. Oh, here is Rolando. Can you give a word about Fabulous, or how was it working with Limbach?
Thank you. Thank you, Sana. So I gave yesterday an introduction for those who were not connected yesterday. So Limbach and Hella are two of our 6 use cases. The Fabulous is, first of all, a European project, but it's more than this. We are building a pilot line. So objective of the project is not really to produce demos, it's to serve the use cases, which are our customers 1.0. So we are building the pilot line, which means that we are setting up all processes in order to have a smooth workflow from design to production. The pilot line is not existing in one single place. The pilot line is a distributed one with 14 members, of which 12 are technology providers. These are companies that are sitting at different places on the value chain. So we are setting up all these projects. As you've seen, for example, for Limbach, getting design from one partner. Limbach is also a partner of the pilot line, then having the origination at another one in PMT, and then the replication at another one. And the objective is that during the first 2 years in the acceleration phase, where we are setting these processes, we are doing this serving the use cases, which were selected out of 6 markets or 5 that have been identified as the hottest markets for free-form microoptics at the moment. So we are sure that once we have done this, which at the end of this phase is end of this year, early 2022, we can serve these markets. And then we will open a second phase, which will be the phase where we'll be testing the business model of the pilot line. We'll be doing this in 2 ways. First of all, with pilot cases. So companies in Europe can apply for this program. If they request piloting services, we analyze their request. If they are chosen, their work will be subsidized on a fund that we have aside. The idea is that we will be working close together with these pilot cases, which are the customer 2.0, in order to test and to learn more on our business model. Because at the end of the project, we want to be also sustainable. And the second pillar of this phase is also serving customers. Actually, this is already started. We are already in discussion with the first customers. So standard customers, not going through any, let's say, special program. And this is something that will go up to the 4th year of the project. And we hope that we will be find magical recipe to be sustainable and to keep this know-how in Europe. And at the end of the workshop today, I will, in the final word, I will say a couple of things more about the importance of the ecosystem. Hope I was quick enough, Sana.
Perfect. Thank you very much, Solen. And thank you again, Ruben, for the excellent presentation.
You're welcome.
So again, let's move on. The next speaker, Laura Lee, comes from Thales Research and Technology Division, which is located near Paris. Thales is a large company specializing in defense and security. That's what they're mostly known for, but they also have many other divisions. And of course, there are multiple applications where free-form micro-optics are used. Today, Laura will share the opportunities, but also the challenges they are facing at Thales. So, Laura, you're welcome.
In this talk, I will speak about different applications for micro-optics and nanostructured optical surfaces at Thales for different domain of applications, from optronics to space. Next slide, please. Can you hear me? Okay. Next slide, please.
It might be that we got a little issue there. I think so.
Okay, thank you very much. So optics are present on for many products for the Thales group and on several domains of applications, from space, avionics, ground transportation to optronics. Today, preparing the next generation of products is also proposing new and disruptive concepts or optical architectures. And this can be allowed thanks to the use of micro-optics and nanostructured surfaces. For instance, here are the main applications for this micro-optics. For instance, for space, we have the flat panel solar array and the Earth observation instruments. For avionics, the applications are sensors or helmet visor. For ground transportation, we are talking now about the autonomous platforms. And for optronics, we are looking for next generation of helmet and next generation of surveillance. Next slide, please. Thank you. What about the role of Thales in the Phenomenon project? We were involved in Phenomenon as a partner for the demonstrator work package. The objective was to evaluate the manufacturing techniques developed within Phenomenon, that is the multi-photon laser writing, thanks to the realization and the evaluation of a demonstrator for a functionalized window. The application was for avionic sensors, but also can be very interesting for autonomous platforms. So what do I mean by a functionalized window? Next slide, please. A functionalized window is a window that has been nanostructured with geometry that mimic the nature, such as a lotus leaf or a butterfly wing, enabling some optical properties or fluidic properties. So you can, thanks to that, you can combine different properties with the same on the same window. You can see the superhydrophobic property, which is well known, so that a water droplet cannot stick on the surface and is ejected out of the surface. For the anti-reflective coating, it's just an anti-reflection property. So within Phenomenon, the chosen demonstrator was not an anti-fogging window for high quality image systems. Next slide, please. Here you can see the sample that has been manufactured by multi-photon optics. On the left of the slide, the structured area is 1 centimeter square on the germanium substrate for long-wave infrared application. In the middle, you can see some scanning electron microscope photograph of the structures that are cones with a depth of 5 micron and pitch of 1.6 micron. You can see that it's very small. The fabrication time for this sample was 23 days, but with a monospot laser. This duration may be decreased by using multispots with our partner IMT Atlantic. Next slide, please. Now, what about the behavior of this sample, this demonstrator after spraying? You can have the answer on the right part of the slide. You can see that after spraying, there is no more droplet on the structured surface. The drops have been ejected out of the structured surface. You can see in the middle, and you can see also on the right picture that there is no drops. Next slide, please. So now the idea to go further is to make an imaging experiment under fogging. Here is the demonstrator principle. First, let's consider a long-wave infrared camera. You will see on the left the image seen by the camera. Then the next step is to put a standard window in front of the camera and to spray it, and you will see in the middle that the image is blurred and you lose a lot of details. Now, can you click please? Thanks. If you put in front of the camera a window that has been structured, the phenomenon window, you will see that there is no sticking effect. And so the idea is to recover the image quality, to maintain the image quality. Next slide, please. And now the real experiment, the demonstrator, which has been implemented in the Thales long-wave infrared camera. You can see in the middle the camera with a window that is looking to a logo plate, the logo of phenomenon, and you have behind this plate a hot plate in order to image the logo in a thermal vision. Next slide, please. So here is the experiment. We will spray, you can see a video where the water is spraying with a standard germanium window. Can you play the video, please? No, yeah, thank you. So you can see the phenomenon logo, and when spraying, you can see that you lose the image. The water blinds totally the field of view. Next slide, please. So now we have done the same experiment, water spraying with the phenomenon window. You can play the video now, please. So you can see here the logo. And now during spraying, you can see that there is no effect on no loss of sensitivity. And moreover, the demonstrator matches the Thales superhydrophobic requirement with a contact angle higher than 150 degrees. Next slide, please. So this functionalized window is of interest for sensors, for avionics, optronics, or ground transportation. For sensors, the needs are the robustness, wiperless system, and avoidance of complex maintenance. You can see the requirement on the the left part. The idea is to apply to infrared or visible sensor, flat or curved windows. We need robustness or low cost if there is a yearly maintenance. And what we need is today an industrial solution. Would it be MPP, molded glass, or 3D imprint, or other technologies? We have also a short-term needs that came up recently, which concern obstacle detection for autonomous urban rail or metro platform, where the requirements are security, robustness, and yearly maintenance, large volume, and cost of windows. Next slide, please. Here is a slide regarding a second application that was discussed during the Phenomenon project. It concerns micro-optics for space electrical solar generators. Today, the roadmap for new solar array architectures are flexible array panels, which are already under industrialization. The idea is to save volume and weight. Next generation will be flexible panels, but with micro-concentration photovoltaics. It's a more longer-term prospect and has been discussed within Phenomenon with Fluxim. The requirements for this application is, of course, very large surfaces, higher than meter square, molded glass or 3D imprint of glass, flat, curve, or flexible optics. Next slide, please. Here is another application which was not discussed during the phenomenon project, but it's an application that is of interest for Thales. It concerns the helmet for avionics or optronics, where we need compactness, mass reduction, ergonomics, and vision comfort. Two solutions are possible for these helmets, the freeform visor on the left part and the pupil expansion. Regarding the freeform visor, the requirements are, of course, lightweight component. We would like to have continuous freeform with 100 to 200 micron deviations from sphere, and also low cost availability. Regarding the pupil expansion, it consists of micro optics, which are also freeform optics, which are lightweight and very, very compact, enabling very, very compact optical system. We would need microstructured freeform on molded glass or plastic, and of course, going from low cost to ultra low cost to increase the market. So the question we have is today is which technology could be interesting, could be used for ultra low cost possibility. Next slide, please. So this is my last slide, a conclusion summarizing many applications for freeform optics. Here are the main applications that we can focus on that are very interesting for Thales. First, regarding space, the big interest, which is a long-term interest, but it's very interesting for Thales, is a MLA for photovoltaics microconcentration, where we will need very large size components and going towards flexible. In the middle, we have some applications regarding windows for sensors, for ground transportation of avionics, dedicated for infrared or visible application on flat or curved surfaces. And we need robustness or low cost if we decide to go to yearly maintenance. Then there are also other applications in the avionics or optronics domain for pupil expansion, where we need low-cost components, molded glass or infrared glasses. And in terms of optical components, we will need molded optics, also glass or infrared glass, on flat or curved substrates, and it would be also continuous freeforms. Next slide, please. Okay, so thank you very much for your attention. My contact email is given in this slide, and if you have any question or any solution to provide regarding the technology, I am very happy to discuss with you.
Thank you very much, Laure, for the presentation. And as you showed, there are multiple opportunities for micro-optics. Any questions for Laure from the audience?
Laura, this was a fantastic talk, and I have to tell you, you have to speak at one of EPIC OTM's online technology meetings to get more interaction with the people from molded optics or 3D printed optics and more fabulous partners, people who can help you with coating. Oh, I see maybe Rolando want to say something.
Yes, just wanted to say, so it's very interesting, the field of MLAs for micro concentration for photovoltaics on large surfaces. It's something, an area where Fabulous could help. We identified energy photovoltaics is one of the markets. We are not, it's not at the moment our highest priority, but if you want to discuss further, please don't hesitate.
There is also a question I see from Moveo. Andre? Yeah, Andrea? Yeah.
Yeah. Hi. I was also actually wondering about the photovoltaics. How large is the size you expect? What I've seen was a space application, but are you also thinking about panels deployed on a very large scale?
Yes, we are thinking about, you have some, on slide 12, you have some example of what we need. It's for, we are, at Thales, we are focused on the space applications. So for satellite wings, it's something like meters, squares, large panels. And the idea is to, if you can combine both the micro lens array with the on a flexible panel, it will be very nice.
Thanks. Can I ask one more question actually regarding the visor parts you showed?
Yes.
They appeared, at least in some of the images, there appeared to be parts which have features on both sides, look to be like a light guiding optic. And can you comment on how large these parts are and what the required alignment accuracy between two features on opposing sides is?
I would, sorry, I would not be able to give you all the details for the moment. You are, if I understand correctly, you are talking about pupil expansion solution. Is that right?
I was referring to your slide on that, and on that slide, I think on the there was one part that looked to be like an ocular kind of part, but another part which looked to be projecting light into the user's vision system.
Yes, there are two solutions that I would say, one which is compact using continuous freeforms, and one generation that we would go into it, which is based on pupil expansion, which would enable something like which is more compact, but with using kind of wave micro optics and acting as waveguides. But I don't have all the details about the precision on the micro optics. So,
Andreas, perhaps it's also a good idea just to contact directly, and then you can discuss on the details.
Yeah,
so
maybe we can do something interesting.
Yes. Let's move on to our next speaker. First of all, okay, also sorry, Laura, thank you very much for your presentations. And let's go into the next speaker. And he is Derek from Design LAD. Design LAD is a lighting technology company from Scotland with a focus on automotive and commercial lighting. Derek's activities are around new materials, new technologies and processes. So let's hear what exciting topics Derek will share with us today. And Derek, don't worry about the time, we still have plenty, no need to rush.
Good morning, everyone, and thank you, Pia, for the introduction. Is the shared screen coming through okay?
Yes, perfect.
Okay, so as you say, I'm here to talk about design-led and design-led's involvement in Phenomenon. We've got a use case partner in the Phenomenon project. I'm actually not going to talk too much today about the results from the Phenomenon, more a discussion of design-led, our use of freeform optics, both micro optics and macro optics, and the challenges that we see when working with micro optics. So just a quick overview, a couple of slides on Design LED. We're an LED lighting technology company with an automotive focus. This is going to echo some of the content that Daniela was presenting earlier this morning. So we have well-established LED light guide technologies, introducing LEDs across a large surface area for the backlighting or direct lighting of materials. And in the past, we've used both macro optics and micro optics distribution across the surface that extracts light from a light guide and delivers the light dynamically across the surface. Design-led, as I said, we're a technology company. We're based, as you can tell from my accent, we're based in Scotland, just outside of Edinburgh. 15 employees, real focus on technology and technology development. That since 2004, that's led us to create 68 granted patents in optics and HMI, really driving towards cost-effective, differentiated, and really attractive illumination and smart surfaces. And over the last 4 or 5 years, we've transitioned to this focus into the automotive sector. And this has been from clear and consistent demand from the automotive industry that is the future, that is what they're looking for. And their interests are in things like perfect uniformity across the surface, to illuminate surfaces and go around obstacles. Nowhere within a car is a perfect rectangle. And obviously they need to do so in a format that is thin and space efficient. More recently, we've worked with using smart LEDs and other technologies to create dynamic RGB effects. More and more, we're working on HMI, so that's human machine interface applications through the integration of switching technologies. And of course, we're doing so with a view to manufacturing for the automotive industry, where cost is a factor. So of course, we need a cost-efficient metric. In terms of our use of optics in the system, we've got different uses for introducing optics onto a light guide. That can be for light extraction, typical use of optics on a light guide, as you can imagine. And the other area that we're interested in is LED concealment. We do not have an edge-lit technology. This is LEDs distributed across the entire surface. So the LED packages themselves can potentially be visible. So we want to conceal those LEDs and reduce the appearance of those and the artifacts that those would introduce. We've got different formats for the extraction optics, both reflective and refractive. I'm not going to read through the list here, but in the past we've used reflective optics as a sort of one-dimensional distribution across the surface. We've also worked with conventional micro-optic films, and I'll speak about those in a bit more in a moment. And then using a technique that we developed and patented, we modified the surface of that of the micro-optic film. And an example of that is shown here. And again, I'll speak about this in a little bit more detail in the next slide. And then more recently, both in Phenomenon and in other projects, we've looked at the redistribution of the optics across the surface to create a 2D pattern, to move from a one-dimensional distribution to a 2D pattern that would fully realize advanced features. So a quick history in our use of light guide optics, quite simply starting with printed macro optics. And then, as I mentioned, using films such as BEF, brightness enhancement film. And here you can see the prismatic structure of the brightness enhancement film. And then in this region, we've locally printed, and this is screen printing technology. So this is high TRL, TRL9, well-established low-cost technologies to print onto the BEF structure and effectively switch off the effect of the prisms. So we locally switch that material off, its optics off, and we are then able to retain total internal reflection locally within that region. And this is something that we've explored, been able to switch on and off the effect of the micro-optic film. We've also worked both within the Phenomenon project and directly with CSEM on customised micro-optics. And just as John was talking about in the talk earlier today, where there's a need for combining optics, photonics and other technologies, more recent innovations have been focusing in printed electronics and the use of advanced LEDs such as smart LEDs, etc. Typical use cases, obviously in the automotive sector, we can't go into too many customer applications, but typical use cases we would have for the optic would be in a large scale large area scalability, should I say, dynamic RGB across the surface, making parts that are segmented, that leverage some of the challenges and trends that Daniela was talking about in terms of miniaturization and controlling the homogeneity across the surface. You can see here, this is our demo for a trade show of the same type of application space that Hella have developed, where you have discrete LED parts laid out in a layer structure. So, and again, this is the same sort of application space where it's a tail light for the automotive industry. And then other areas such as hidden to lit appearance and segmentation. So a short video now, and I'm really hoping this will play on the technology. So we add printed electronics and printed optics and encapsulate the LEDs in a transparent polymer, and then add the concealment optic onto the polymer. When it's combined with a reflector and a diffuser, this creates a light guide with the LEDs distributed across the entire surface, and the properties of the optics on both upper, lower and surfaces create LED concealment and light extraction across the surface. Our use of macro optics, so before I get to talk about micro optics, our use of macro optics, and this is really about being able to create product that we can deliver to the market today, that has focused on screen printed inks applied to the surface in 1D patterns, and then, as I mentioned a few moments ago, more recently 2D patterns. Those could be for side emitting LEDs, but they could also be for 360 degree or polar LEDs. So the LED itself is actually located at the center, and then there's a radial polar distribution of optics around the surface. And as you can imagine, we would have other LEDs located around the perimeter of the area of the part. As I mentioned, our use of macro optics is really about leveraging the capability of the higher TRL technologies so that we can deliver today to meet customer demand. When we've used commodity micro-optic films, we've mentioned, previous speaker mentioned about beam profiling. This is an example of the output with a commodity prism film, a BEF film that's actually used. Our use of this material was to use it as the substrate material. So the LEDs would be mounted onto the planar surface, and the light guide is up here where the text is. So the light that's delivered has this highly asymmetric beam profile, light delivered from both surfaces. And interestingly enough, if we introduce a reflector into this, we can flip this lobe and bring this lobe down and essentially strengthen the output. But it's somewhat counterintuitive that we have an asymmetric light distribution from a symmetric film. This becomes even more interesting when we look at other films and other prism shapes. For example, an image directing film, an IDF film, with a 20-degree prism film. Again, this is an example with a reflector in place, but you can see that the directed light is a broader direction down at this angle, but the orthogonal light that's distributed in 90 degrees to the LED axis is these lobes that are delivered here. So essentially, a rectangular area of component would deliver direct light down at this 20-degree angle, and then deliver light orthogonally on each direction. So you can get very interesting beam profiles and shapes with the use of micro optics. And that sort of led us to explore both in phenomenon and directly with CSEM on the opportunities for custom micro optics to modify the shape, the angles, the dimensions, the pitch. The part of the challenge in doing so is we don't know exactly what it is that we're looking for. We know we want a result, but we don't necessarily know how we're going to achieve it. So there's a degree of experimentation and exploration in doing so. What we're really looking for, though, is a one-dimensional or two-dimensional pattern, a repeating pattern, not a consistent prism shape, for example, but a modification. We want to control the light intensity distribution for diffusion, for beam angle, for beam width, in order to deliver the next generation applications. So I'm just going to echo some of the content that Daniela presented earlier in terms of the automotive industry's need for luminous surfaces. And these are just some OEM examples. You recognize the brands, obviously, and these are current and future vehicles, visions from Nissan, Audi, Bentley, Lexus, Toyota, and there's presentations that have been given in the automotive industry, many minutes devoted to this topic. I'm really going to focus on a couple of slides. In addition to luminous surfaces, there's also a convergence of the lighting and display technologies. Display technologies are traditionally where we found micro optics, but there's a convergence of those technologies as we move forward. So as I said, in the final slide for me, our challenges are identifying an optical structure that is available in the higher TRL format that would allow us to generate a master that we could really drive production of a distributed 1D or 2D optic. Having the type of BEF type film where it's a repeated periodicity has got very limited capabilities in terms of how we want to use it. So we really want to find technologies that would enable us to generate a master for higher TRL applications. And that's my contact details, and thank you very much. If anybody's wanting to contact me directly, then please feel free to do so.
Thank you very much, Derek, for this excellent presentations. And I hope there are a lot of people in the audience who are able to help you with these challenges. I don't see any questions on the chat, but if there are any questions on the audience.
Okay, I do have one. I do have one more thing to mention, and it's just a verbal comment from me. And there's very little I can say on it because it is really just hot off the press this morning. So I'm more or less just going to read the content of a press release. So if you can bear with me for 10 seconds, that today we're very happy and delighted to announce that DesignLED has been acquired by Faurecia. Faurecia is a global leader in the areas across, multiple areas across the automotive space, in seating, interiors, mobility, and in particular in Clarion Electronics. Obviously, this is a hugely important milestone for us. So we hope to be able to accelerate some of the work that we've been doing in terms of all the things that I talked about for differentiated display and backlighting technologies.
Thank you, Derek. Oh, that's big news for design.
Enormous news.
Yes. Thanks for sharing. Are there any questions for Derek, or any one of you who can maybe assist with the challenges and the larger scale micro-optic films? I think you did such a good presentation, so no more questions on that. And I know we're a little bit behind the schedule. However, it was really important to hear what you had to say. Let's have the closing words from the EU coordinator. So potentially Rolando.
Pia, if you allow me, just before we say the final words, I would like to remind everybody about our one-day session. So please don't leave. Pia, just share the link. We will share it again.
Thank you, Sana. Yes. And by the way, if you close the, make sure you click on the link on the chat. Otherwise, when you close the Zoom, then the link will disappear. So either copy it or just click it directly from the chat. So Rolando, final closing words from you.
First of all, thank you again, all the people who have contributed in organizing the workshop. I really would like to thank Pablo, who came to me with the idea of organizing a shared or common workshop. I think it was a very good one. It was a very good way also to cluster among European projects and in the ecosystem. And I would like also to thank all the speakers. Very, very interesting to see all these needs about micro optics that we hope to be able to serve with Fabulous. As I said previously, one word about the ecosystem. What this workshop shows today is that the most important thing we have, let's say the most important element we have in Europe, thanks also to the geographical proximity of the countries, is the ecosystem. We see today that bringing together use case, I would say, end users and technology providers is a winning point, because we bring together needs and solutions, and solutions can be adapted really to the real needs. So this is also what Fabulous is going to do in the next few months. Building the ecosystem is one of the missions we have from the Commission. We'll do this through our website, through what we call the marketplace. It's a place where companies that are, let's say, end users and technology providers can advertise their needs and their offer in a free for, let's say, broader micro optics. And we'll offer this service through Fabulous and in the early phases of the pilot line for free. So my invitation, let's say, my message, take-home message for everybody is to link to Fabulous. We have a page on LinkedIn, link there. You can also link to me, but through the Fabulous LinkedIn page, you will get all the news, and the marketplace will open most probably end of June, early July. And I invite everybody to advertise your company there with your offer. You will see what we require is really concrete offer for the ecosystem. And also, this is also how Fabulous is meant to grow. The second date, the second take-home message for all companies interested to be eligible as pilot cases will be January 2022, where we'll be opening the calls for pilot cases. As you already hear, few companies that may be interesting, for example, Design LED, I didn't mention this, that I signed, for example, in the proposal phase a letter of support for Fabulous, and I'm sure that we can find a way to collaborate through the pilot case program. And that's all from my side.
Thank you very much, Rolando. And Pablo, closing words from you.
Thank you very much. And yes, I want to thank all the team in Fabulous, Rolando as coordinator, and the whole of the team involved in the organization, because you prove us right in our decision of teaming with you, because really our intention was to make a workshop to show the results of the project, and I think this workshop was much more than that. It showed, as Rolando mentioned, how dynamic and exciting the community is around the users, designers, and manufacturers of micro-optics, and how well, when you go to any of the recent meetings around optics or laser or photonics in general, beamforming and light manipulation in custom way is a very hot topic, and obviously optical surfaces and freeform optics is a great tool for that. So we wanted to provide with our project our grain of our contribution to this community with one manufacturing technique, but the scenario open by projects and concepts like Fabulous pilot line shows that this is growing with ideas and with possibilities, and we as a closing project want to be part of the upcoming changes and the upcoming glow of ideas and opportunities. So again, thanks, well, from my side, especially Pia and Patrice for helping me also in the organization from the side of Phenomenon, to all the Fabulous, with pun intended, Fabulous partners in the organization, particularly EPIC in the all the technical and side, and all the attendants, which were a very good community that I hope we will continue collaborating with. And that's all from my side. Thank you.
Thank you, Pablo. And thank you also from my side, Sana, Helena, Jessica, and everybody who were making this workshop possible. What a wonderful workshop and abundance of knowledge we shared. It's been great to be a host today. And thank you everybody who participated. Please join us at the WonderMe session. It'll be nice to talk to you a bit more. Use the link provided at the chat. And from my side, Sana, Helena, any words that you want to say?
I would like to shout out to our team at EPIC. Elena, Jessica, this would not be possible without your support. And my wonderful co-host Pia from CDA, and all the Phenomenon and Fabulous teams. Again, if there is, for all the participants, there is a way to join more technology meetings where you can connect with other people and other partners via the EPIC online technology meetings. So go to EPIC website and you will find all about it there. And otherwise, to contact Fabulous or to contact Phenomenon, you can either reach out to EPIC or reach out directly to Pablo and Rolando. That's it from my side. Thank you again, Pia.
Thank you. And we are done now with the workshop. See you at the WonderMe.
Bye.
Bye-bye.
Bye-bye. So I will be on the other side, and everyone else, please open the link first and then go to the WonderMe.